talk about the Fourier series representation of discrete time periodic signals, and you'll see that this discussion will have a very close parallels with the discussion of Fourier series representation of periodic continuous time signals. But however, beside these parallels that we're going to draw between continuous time series, Fourier series, there are some important differences that one should know. So, well, first of all, you will see that what happened in continuous time Fourier series representation was that we were using harmonically related complex exponentials to represent continuous time periodic signal. Over here, well, we're going to use these discrete harmonically related complex exponentials. Well, but the difference is that this series is finite. It's not infinite. Okay. So in particular, the Fourier series representation of a discrete time periodic signal is a finite series as opposed to an infinite series representation of a required for continuous time periodic signals, and as a consequence of which there are no mathematical issues of convergence, okay, because we are looking at a finite series which is convergent by all means. So why do we have finite series is due to the fact that there is a limited range of harmonics which can reconstruct a discrete time periodic signal. Why? Because after the period, let's say capital N, which is a positive integer for a periodic exponential, the harmonic, the complex exponential tends to repeat itself. Okay, I mean the complex exponential is already in terms of sine and cosine, and they tend to repeat. So you don't need to consider an infinite harmonic index. Okay, so let's develop this understanding again in terms of just as we did in a very similar manner as we did for continuous time periodic signals. So let's consider linear combinations again for harmonically related complex exponentials. These exponentials will be discrete in nature. Well, they have to be, of course. But so if you recall in chapter 1, we talked about that if a discrete time signal xn is periodic, then it must have a period which is a positive real and an integer quantity. It has to be a positive integer quantity, and it must satisfy the following relationship. Okay, that is a discrete time sequence. For a discrete time sequence, if it is periodic, there must exist a positive integer capital N for which the relationship holds. This relationship holds. Okay, so the fundamental period again is the smallest positive integer n for which the above equation holds valid, and omega naught over 2 pi by n is the fundamental frequency. So as an example, if you consider the complex exponential, discrete exponential of the form ej 2 pi by capital N small n, then it is periodic with period n. And how you show this is periodic, we can again use the same definition of periodicity for a discrete time sequence. So if you use this definition, if you use this definition to show that this sequence is again the complex exponential sequence is indeed periodic, all you need to do is to replace sequence by capital N plus n and see if this comes n equal to x of n. So if you do that, then okay, this 2 pi over here, you note that over here this is of the form ej omega n, and this 2 pi by n is nothing but frequency. So let's replace n by capital N. And see the picture over here. There will be two. It can be exponentials to two exponentials. So one of the exponentials is indeed x of n. It will be of the form ej 2 pi by capital N into small n. N is the discrete index of the samples. And then another exponential that's going to come along with it is ej 2 pi. That's it. ej 2 pi. Why? Because this quantity when multiplied by capital N is ej 2 pi. And if you can see this exponential in terms of sines and cosine, then cosine 2 pi is 1 and sine 2 pi is 0. So this first exponential is unity. It's 1. Okay. So this is your x of n. This is xn plus n. Therefore, the sequence we can say is periodic because it satisfies this relationship. So the sequence is periodic for which we have a smallest positive integer capital N that satisfies the above relationship. Okay, so this is about the an example of a discrete time complex exponential sequence. We're going to use the harmonically related such complex exponential sequences to develop the Fourier series representation of our discrete time periodic sequence. Okay. So furthermore, the set of all discrete time complex exponential signals that are periodic with period n are given by are given or whatever here. Let's denote them by phi k of n. Okay. And omega naught is the frequency. So k represents the harmonic index for a discrete time complex exponential sequence, and they're all periodic with period n. Okay, so k is ranging from 0 to plus minus 1 to plus minus 2. So you see again, if you replace over here n plus capital N, you're going to end up in the same sequence. That is your original ej k omega naught n. Okay, k being the harmonic. So the harmonics are being related. So for example, k, if k is 1, then this is the fundamental. K is 2, so then you have the second harmonic, third harmonic, and so on and so forth. All of these signals, they have the fundamental frequencies that are multiple of 2 pi by n, and thus are harmonically related. Okay, so k over here is the harmonic index. As you can see over here, k is the harmonic index. Omega naught is the fundamental frequency. Okay, and k is varying as such. So now there are only n distinct signals that you see over here in the given set of in the set given by the above equation. This is the consequence of the fact that the discrete time complex exponentials which differ in the frequency by a multiple of 2 pi are identical. Okay, so exactly what happened, you see over here, if you're going to add capital N, which is the period, then that means the sinusoids are there's a difference of 2 pi in the sinusoids, and the same relationship repeats itself, so it becomes x of n. Okay, so in the case of complex exponential sequences, if there is a difference of 2 pi, a multiple of 2 pi, you get the same sequence itself. Okay, so the discrete time complex exponentials which differ in frequency by a multiple of 2 pi are identical. Okay, so specifically this means in terms of the harmonic indexes. For example, you can see over here from this relationship, phi of 0. Well, phi of 0 is what? It's 1, right? K equal to 0 is 1, and that is equal to capital N as well. Okay, if k is equal to capital N, then this n cancels with this capital N, and you're left with ej k 2 pi by n, right? So for example, ej0 is the same as ej of k 2 pi by n into capital N, right? Why? Because this is 1. Okay, so this n is going to cancel out, and then integral multiple of 2 pi, cosine of integral multiple of 2 pi is what? It's 1. Okay, so these two exponentials are the same. Okay, they're giving the same result. Again, these two quantities are equal. Similarly, for the harmonic index of k equal to 1 is the same as the harmonic index capital N plus 1. That means because you see again the difference in the frequency that comes over here, in both cases you will see the difference in frequencies will be 2 pi. Okay, so that means in this range there are only n distinct signals. Okay, because after 2 pi the sequence become identical. So for example, what we are doing is, so if you have the index for this, so this is for k equal to 0, this is k equal to n, and then for k equal to 1, this expression will be of the form 2 pi by capital N to small n, and if you're going to compare k equal to 1 to capital N plus 1, then this can be written as ej 2 pi by n capital N into n plus 1. So again, you are going to have, you can bifurcate this exponential into 2. Okay, so basically you will have an expression, you will have ej 2 pi, okay, this n cancels, and then again we'll have ej 2 pi, ej 2 pi by n, okay. So you again see that this is nothing but unity, okay. This is equal to 1, okay, this is equal to 1, and then again these two expressions, they're repeating again, they're going to repeat. So the thing is, you don't need to go beyond a limited range of region for the harmonically related exponentials. I mean, it will be suffice to consider, for example, the range k from 0 to, let's say, capital N minus 1. This will consist of capital N number of harmonics, or alternatively, you can have a range of k's for, let's say, k to capital N. Okay. Again, these are their capital N number of samples. I mean, there's a multitude of such limits. For example, if you're going to, if you have to start with 2, then that will be from k to capital N plus 1. Okay, because k equal to 2, if you're going to substitute k equal to 2 in this complex exponential sequence, and then compare it with n plus 1, well, there will be, n plus 2, there will be repetition. So it suffices to consider the range of from k equal to 2 to n plus 1, or k varying from 0 to n minus 1, because 0 and n are same. 0 and n are same. Similarly, 1 and n plus 1 are same. So you don't need to consider n plus 1 in this range. Okay, you don't need to consider n plus 2 in this range, because n plus 2 is 2. Okay, n plus 1 is 1. 0 is capital N. So we are not going to, let's not consider those harmonics, because the exponentials are going to repeat for themselves. So in general, we have phi k of n equals to phi k plus Rn. Okay. So that means when k is changed by an integer multiple of capital N, the identical sequence is generated. Well, that's expected, because you are repeating the sinusoids, right? You're repeating the sinusoids. So n happens to be the integer of the discrete time sinusoids, and n happens to be the integer. So Rn is an again integral multiple of those integers. Okay, so that is expected. So this differs from the situation in continuous time, in which the signals that we consider for harmonic relationship were of the form phi kt, defined as follows, and they are all different from one another. I mean, ej k omega naught t is ej k 2 pi by t. Capital T is the period multiplied by small t, and for this there's no limit. I mean, it doesn't repeat after. You don't need to consider a range like this. You don't need to consider a range like this for continuous time periodic signals. This range is only applicable for discrete time sequences. So that means if you have to express your Fourier series discrete time, if you have to represent discrete time periodic sequences or signals in terms of discrete time Fourier series, the range of region for harmonics are limited. Okay, it is a finite range, so then it turns out to be a finite series as well. Okay, which was not the case over here. There was no limit on k. Okay, I mean, each value of k is independent of each other, right? First harmonic, second harmonic, but over here, for example, the first harmonic is the same as n plus 1th harmonic. Okay, so these two expressions are the same. These two expressions are the same. Okay, similarly, k equal to 2 is the same as kn plus 2. Okay, so you don't need to repeat for exponentials or repeat the same patterns. So the discrete Fourier series you will see is going to be a finite series, and there won't be any convergence problems. So we now wish to consider the representation of more general periodic sequences in terms of linear combination of such sequence phi k of n. Now such a linear combination has the form. So x of n is the general periodic discrete time signal satisfying xn equal to xn plus capital N, where capital N is the period. Then we have a series. Okay, we have a very similar series as we had before for continuous time Fourier series. The summation is over k. K is the harmonic index again, and phi k of n are the complex exponentials. Okay, ak are being the Fourier coefficients, which are the strengths of these exponentials. So in a very similar manner, you can have this as in terms of the complex discrete exponentials ej k omega naught n. Okay, where omega naught is nothing but 2 pi by capital N, and capital N being the period of the discrete time sinusoid, and the sequence x of n. Okay, So uh, so this is again Fourier discrete time Fourier series representation of x of n in terms of harmonically related complex exponentials. Okay, and these exponentials are coming with their weights or their strengths, which are given, which are also the spectral components of or they are called as Fourier coefficients. Okay, or strengths of the corresponding harmonics. Okay, but these harmonics you will see are finite harmonics. They're not infinite. So this summation is not varying from minus infinity to plus infinity. Okay. So since the sequence phi k of n are distinct only over a range of capital N, so successive values. So over a range of n successive values of k, the above summation need only include the terms over this range. Okay. So we just need to consider the successive capital N number of samples for the harmonic indices. Okay, that is k. So we need to consider the consecutive capital N number of harmonics. That's it. So what we do is, so thus the summation is on k, and as k varies over the range of n successive integers, beginning with any value of k, we indicate this by expressing the limits of summation as k as capital N. This in some texts is also referred as the average value, but anyways, over here this means we are just referring to the successive capital N number of harmonic indices, okay, which are consecutive values. So if you are going to start with k equal to 0, then the next one is 1, 2, 3 up until capital N minus 1. Similarly, if k starts with 1, then you have to go all the way to capital N. Okay, so it's not like you go beyond beyond the range of vision. It's just the successive values. Okay, the subsequent values. So x of n over here is being represented by successive values, capital N number of indices. Okay, for which the complex exponentials are periodic. Okay. AKs again are the strengths. So if you expand this, well, you have the same expression in terms of the complex exponential sequences. This is a discrete time Fourier series. So for example, k could take on the values k equal to 0, 1 up until n minus 1, or if it starts with 3, then you know that n plus 3 will be the same as 3. So the successive values, capital N number of successive values, they have to end up till n plus 2. So in either case, by the virtue of phi k of n, which is a complex exponential that is periodic, you will see that you only need to consider the finite number of complex harmonically related exponentials. And again, x of n is being represented by a linear combination of such harmonically related exponentials with their corresponding strengths ak. This is the definition of the Fourier series. Okay, so exactly the same set of complex exponential sequences appear on the right hand side of the above summation. So the above summation is referred to as discrete time Fourier series, and the coefficients ak are the Fourier series coefficients. Now, a natural question that should come at this point in time is how to determine these Fourier coefficients. Okay, now we know that the series is finite. Okay, it's not infinite. So how to determine these finite number of coefficients? Okay, the coefficients are also finite. Why? Because we are considering only the finite number of harmonics. So of course the coefficients will be finite. How to determine them? Now, suppose that we are given the sequence x of n that is periodic with fundamental period capital N. We would like to determine whether the representation of x of n in discrete Fourier series exists, and if so, what are the values of the coefficients AKR? Okay, so this is again a finite Fourier series. So this question can be phrased in terms of finding a solution to a set of linear equations. Well, why they are linear equations? You see, if you expand this over k, you will have a set of linear equations, okay, where AKs are the unknowns, okay, and you can expand this in terms of harmonically related complex exponentials. So for example, specifically, if we evaluate the series for n successive values of n corresponding to one period of x of n, we obtain, so for example, what we're going to do is we're going to expand x of n, okay, over n, and we're going to expand this series over k. So when you're going to expand it, so starting from n equal to 0, the summation is of the form k equal to n. Okay. Over this range, the exponentials are constant, they're all unity. This is ak. Then x of 1 is 2 pi k by capital N into 1. Then n minus 1 is, you just replace small n by capital N minus 1, so which appears over here, right? Divided by capital N. So the situation is like this. You have a set of linear equations in terms of, these linear relations are in terms of the harmonically related complex exponentials. Okay. For example, the sequence is periodic, so we are considering one period of the sequence x of n, okay, because capital N is the same as, is going to be the same as x0, right? So this is the left hand side in the matrix form, in the row vector form, and then on the right hand side we're going to have the Fourier coefficients, right? So for example, x0 will be a0, a1, all the way up to dot 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 dot. This will be a of capital N minus 1, right? I mean, this is the expansion. This was the expansion. If you look at this first equation for x equal to 0, well, this is the expansion, a0, a1 up until an minus 1 for a finite series consisting of capital N number of Fourier coefficients. Okay, and what does this multiplies is the Fourier is the complex exponentials. Okay, similarly for the case over here, over here you're going to expand the summation over again the same finite number of harmonics. So it's again going to start with a0, a1 up until an minus 1, and it's just that you're going to have exponentials like this, e of j 2 pi by n. This is for n equal to 0, so this is for n equal to 0, so this is k times 0, and then you are going to have again exponentials, or I can write this as phi of 1, phi of 2. So this continues. Okay, so these, you can see these are the linear set of equations. Okay, so there is a lot of there's a lot of terms in the very limited space. We can write this again. So let me put this over here. So x0 is my, if you write these equations as a0 plus a1 plus dot 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 plus an minus 1, then x1 is written as, since n is 1, so you just consider that n over here is 1 in this summation. So this again starts with a0 plus a1 exponential ej 2 pi capital N, and this is k. Okay, so k is also 1, right? So starting with k equal to 0, k is 0 over here as well, then k is 1, n is also 1, and then this continues plus dot 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 plus this will be a of n minus 1, strength of n minus 1 harmonic, into ej 2 pi by capital N, and k is n minus 1, right? K is n minus 1. Let's forget about this. I think this is not right. There's some problem. Let's expand this as a series, as a Fourier series, okay, in terms of the definition. So x of n minus 1 will be equal to since now over here small n is n minus 1, so this is again a naught starting with k equal to 0 plus a1 e of j 2 pi over n. K is 1, but then you will have this term n minus 1 over here. Okay, and the last term will be the strength of again plus dot dot plus capital okay, the Fourier coefficient of n minus 1 harmonic into exponential of ej 2 pi by n, and this Fourier coefficient is of n minus 1, so there will be, since small n is also n, so it will be n minus 1 whole squared, right? N minus 1 whole squared. So this is the story, okay? And well, you can go and express this in terms of a matrix form if you so desire. For example, the mistake that occurred in this matrix representation was, if I can do this again. So let's see if we can construct this terms again. Space is not much, but let's see if we can do this. So if you see over here, your left hand side is okay. Okay, this corresponds to the vector of the sequences in the sample, and your Fourier coefficients are going to come on the other side. Okay, so for example, this is going to be 1, 1, dot 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 1, and this will be a naught. Then you're going to have a1. This is a1. K equal to 1. Okay, then dot 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 a of n minus 1. So note that this expansion is over n. Okay, so we are expanding this over n, and over here the expansion is over k. And on the column vector on the right hand side, the expansion is over k. And for the second equation x1, well, this is again 1. Then you are going to have the terms ej 2 pi by n, and then dot 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 this will be ej 2 pi. This is, you note that this is for small n equal to 1, 2 pi by n multiplied by n minus 1. So this is multiplied by n minus 1. Okay, so I don't have much space, but anyways, you can see what is going on. So this continues. So again, the first term is a naught over here, so 1, and the second term will be ej 2 pi by n into n minus 1. Okay, and then the last term will consist of an exponential ej 2 pi n into n minus 1 squared. Okay, so all you need to see from here is that this matrix is a full rank matrix. That is, it has all the columns that are linearly independent. That means you are going to have a unique solution for your Fourier coefficients a case. Okay, where k is ranging from 0 to n minus 1. K is ranging from 0 to n minus 1. So either you can invert this matrix, you can bring this to the left hand side, find the coefficient from the samples, because you know what the samples are. You can find what is ak, right? Or you, from this linear combination, you can go on reducing the matrix, okay, and find what is in terms of x0 and x1 and xn minus 1. You can find the coefficients uniquely. Okay, so it's these columns of the matrices are linearly independent. So you're going to end up in a unique solution for the Fourier coefficients. Okay, this is one of the way to look at the solution to determine the Fourier series coefficients. So you see again, these represent a set of n linear equations for n unknown coefficients as k ranges over a set of n successive integers. So it can be shown that this set of equations are linearly independent, and consequently these can be solved to obtain ak's in terms of the values of x of n. Okay, now this is one way to look at this problem. The other way is if you follow the same steps as we have done before for the evaluation of Fourier series coefficients for the continuous time case, following the steps parallel to those using continuous time, it is possible to obtain a closed form expression for the coefficients ak in terms of the values of the sequence of x of n. So now we consider an arbitrary sequence. Well, the sequence was arbitrary in the first case as well, but we consider x of n and we try to find the exact expression, okay, for ak that is unique in terms of an arbitrary sequence x of n. The basis for this result is going to be from the fact that if you consider the summation of exponential, well, this result is capital N provided that k is 0, plus minus n, or plus minus 2n. Well, what does it mean is that we're just summing up a constant. You're summing up a constant capital N number of times, so the result is capital N naturally. Okay, so for example, k equal to 0 is 1. K equal to capital N, you're going to cancel this capital N from here. You're left with ej 2 pi n, which is 1 again. Similarly, ej 4 pi n is 1, ej 6 pi n is 1. So you sum it up for a capital N number of times, the result is n. Okay, but on the other hand, if k is not equal to 0 or k is not equal to plus minus n, then this result is 0. Intuitively, it means you're summing up the samples of a sinusoid function. You're summing up the samples of a sinusoid function over one period. So what result do you expect? Okay, you see, the point is that if you're going to sum this up over one period, the same number of samples which are there in the positive half cycle are there in the negative half cycle. So they're going to cancel, right? So if k is not 0, not capital N, not 2n, so you don't have a constant, you're just going to sum the samples over one period of a sinusoid or a cosine, the result is 0. The result is 0. So we're going to use this mathematical fact to find the closed form expression for the Fourier coefficient. The above equation states that the sum over one period of the values of periodic complex exponential is 0, unless the complex exponential is a constant. Okay. So let's consider the Fourier series representation. You see, multiplying both sides by e minus j. R is again a dummy variable. So if you multiply that Fourier series, this is Fourier series expansion, finite Fourier series in terms of Fourier coefficients and the harmonic and the exponent and the harmonically related exponentials. If you multiply both sides with e minus j r 2 pi n, and then you sum it over capital N terms, that is, you multiply both sides by this term, then sum it up over capital N number of successive terms. This is how the left hand side looks like. Then the right hand side, you can combine this exponential with this exponential, and then you will have k minus r. And then since these summations are independent, one summation is over k, the other summation is summing up over n, you can interchange the operations. You can bring the Fourier coefficients over here. So from here, you can rearrange your terms like this, and then you can bring this summation forward. The summation is over n, there is small n over here, and again from the same mathematical artifice, well, this we can use the result to what we have over here. This is a very similar expression, and what it means over here is that this will be capital N if k is equal to 0, plus minus n, plus minus 2n, or it is 0 otherwise. So intuitively, the innermost sum on n, this is the innermost sum on n. On the right hand side of the above equation is 0 unless k minus r is 0 or an integer multiple of capital N. Therefore, if we choose the value of r over the same range as that for which k varies in the order of the summation, that is, if k is equal to r, well, then this summation is capital N, right? So this becomes n times a k's, right? And you can bring this n over here in the denominator. So 1 over n comes over here if you're going to bring this the other side. So you're left with the Fourier coefficient on this side only, right? So the innermost sum on the right hand side of the above equation equals n if k is equal to r, and it is 0 if k is not equal to r. So the right hand side of this equation then reduces to NAR, and therefore we have the closed form expression for the Fourier series coefficients, which are for discrete sequence as 1 over n, and again a finite series because we are talking of finite number of complex exponentials. So this is the case. Okay. So this is x of n e minus j r 2 pi capital N small n. Okay. So this provides a closed form expression for obtaining the Fourier series coefficients, and we have a discrete time Fourier series pair. Okay. So this is the synthesis equation. Again, this is the analysis equation. You can bring back k over here. Okay, it doesn't matter. K and r are integral variables. So these equations play the same role for discrete time periodic signals as that for the continuous time signals, and the synthesis equation and the analysis equation. This is your synthesis equation, and the second one is the analysis equation. So as in the continuous time case, the discrete time Fourier series coefficients A, K are often referred to as the spectral coefficients of x of n. They are giving you the strength of the harmonics that is contributing into the signal. And then again, these coefficients specify the decomposition of x of n into n harmonically related complex exponentials. Now, one more thing, referring to the Fourier series, again, this is your Fourier series expansion in terms of complex exponentials. We see that if k is in the range of 0 to n minus 1, you can go on expanding in terms of Fourier coefficients and exponentials like this. Then if you compare this with the range 1 to n, well, you obtain this expression. Okay, so from 1 to n we have the expansion of Fourier series is like this. It's given in the second expression. And now since phi naught n is phi of capital N, so over here you see this term is same as this term. And phi 1 of n is phi of n plus 1. So phi 1 of n is phi of n plus 1, which is going to come after this term, n plus 1. And therefore, upon comparing the above two equations, we conclude that a naught is also a of n, right? So now the thing is, these two expansions are representing, these two expressions are representing the same periodic sequence x of n, right? In which what it is saying is that phi naught n is phi of capital N small n. Okay, that means if the only difference in between these two expressions, this is already contained over here. So this is the previous term of capital N. Okay, so we have the entire term, this much term, which is preceding this term. Okay, the only difference is a naught and phi naught n. Okay, so this term is missing in this term. Okay, so but we know that phi naught n is same as phi of n capital N, right? Therefore we can conclude that a naught is same as a of n, right? Well, this was missing, but this in this expression, in this expansion, we don't have this term. We don't have this term, right? We don't have this term over here. So that means this expression, this circled expression of an, phi n, and a naught, phi naught n, which is the only difference between the two expansions, they are the same, because we know that phi of n is phi naught of n, right? Therefore, a of 0 should be a of n, and this is in general true. This is in general true. Similarly, by letting k range over any set of n consecutive integers, we can say that ak are ak plus n. That means the Fourier coefficients are also periodically related. Fourier series coefficients are also periodic in nature. So this is what we were doing. We were expanding this in terms of Fourier series, and it turns out it's not only the complex exponentials, but their strengths or the Fourier coefficients are also periodic in nature. Okay, which is quite evident by looking intuitively into these two expressions. Okay, so the only difference was these two terms, and these two terms, they have to be equal, so they represent the same sequence x of n, right? So if they are the same, and we know that phi naught of n is phi n, then that means a naught should be equal to a of capital N. That means that your Fourier coefficients are also repeating. They are also repeating. So that is, if we consider more than n sequential value of k, the values of ak, they repeat periodically with period n. So it's not only the complex harmonics, complex exponential harmonics that are repeating. The Fourier coefficients are also repeating with them in the same manner. So that's why the representation of a discrete time periodic sequence is finite. Okay, so it's important that this fact should be interpreted very carefully. In particular, since there are only n distinct complex exponentials that are periodic with period n, the discrete time Fourier series representation is a finite sum with n terms. Okay, because after that, the Fourier coefficients, the strength of the harmonics, they're going to repeat, the exponentials are going to repeat, so we have a finite series. Therefore, if we fix n consecutive values of k over which we define the Fourier series, we'll obtain a set of exactly the same n Fourier coefficients. On the other hand, at times it will be convenient to use the sets of n values of k, and consequently it is useful to regard Fourier series as a sum over any arbitrary sum over an arbitrary set of n successive values of k. For this reason, it is sometimes convenient to think of ak as a sequence defined for all values of k, but when only n successive elements in the sequence will be used in the Fourier series representation. Okay, so where only n successive elements in the sequence will be used, therefore you are going to have a finite number of Fourier series coefficients as well. So as an example, this is from your course text, example 3.10, this illustrates this idea. So for example, if you consider a discrete version of sine omega t, sine omega naught n, over here x of n is periodic if 2 pi by omega naught is an integer or ratio of two integers. You know that, okay? So if omega naught by 2 pi is a ratio of two integers, the sequence is periodic, otherwise it's not. For example, sine 3n is not periodic. Okay, sine 3 pi is periodic, sine 3 pi n. So for the case when 2 pi by omega naught is an integer n, that is when omega naught is given as such, that's the fundamental frequency, xn is periodic with fundamental period n. And we obtain a result that is exactly analogous to the continuous time case. So if you expand the signal in terms of two complex exponentials, well, this is the expansion. And if you compare this with the Fourier series expansion, you can see we are talking of, so we have over here, k is 1. This term is for k equal to 1. And this term is for k equal to minus 1, right? So only two harmonics are there. Well, basically, it's one harmonic, k is plus minus 1. So again, you have a1 is 1 over 2j and a minus 1 is minus 1 over 2j, and this is quite evident, and this you can see this by inspection. So it also implies that ak is 0 if k is not equal to plus minus 1. So there is no DC, okay, because it's a, again, it's a complex. It's not a complex. It's a sinusoid sinusoidal sequence. So there is no DC. A naught is 0. That is expected. So you can see the Fourier series coefficients, but the important thing to illustrate over here is that, as described previously, these coefficients, they repeat with period capital N. Thus, an plus 1 is the same as 1 over 2j, and an minus 1 is minus 1 over 2j. Okay. So the Fourier series coefficients for this example with n equal to 5 are illustrated in figure below. Okay. So what it means to say is this coefficient is same as a of n plus 1, right? An plus 1. So so a1 is an plus 1, and similarly n minus 1. Again, if you are going to add, I mean, if you go beyond n sequences for here, this is same as a of n minus 1. Okay, so we are going to limit our range of region to capital N number of harmonics. So the fact that they repeat periodically is indicated in this figure. So you see that this is a1, this is a minus 1, and you can see the values. This is 1 over 2j, and then you have minus 1 over 2j over here. And we are considering a sequence with capital N equal to 5. So you see at 5, the same thing repeats. Okay. So at n minus 1, that is 4, and at n plus 1, 6, we're going to have the same strengths over here. So these are the same strengths. Similarly, an integral multiple of 5, that is that's coming at 10. So n plus 1 is 11, and then n minus 1 is again 9. 2n plus 1 is 11. 2n minus 1 is 9, and same thing repeats over here as well. Okay. So the Fourier coefficients are repeating. So this is an illustration of a sequence, the Fourier series of sine 2 pi 5 by n, where the period is capital N, that is 5. The period is 5, and the Fourier coefficients are repeating. Okay, that's the idea behind the periodic nature of the Fourier coefficients as well as the harmonically related complex exponentials and the finite series representation of a continuous time periodic discrete time sequence. That's all.